A hydraulic hose is not a pipe. It is not just transmitting a fluid. A hydraulic hose is a power transmitting machine element. And this is why the hose selection becomes critical to transmit the power while bending, vibrating, heating, cooling and aging over the time. This video is sponsored by Brilliant. I will share more about them towards the end of the show. So hi there, this is Ayush from Master Hydraulics today. And in this video, we will learn everything about hydraulic hoses selection. That is how to calculate the hydraulic hose sizes for pressure line, return line and suction line. We will also learn how to correctly select the pressure rating of each of these lines. Because yes, all these lines operate at different pressure. And then finally, to select the exact part number of hoses from hose manufacturer catalog, we will also understand the different hose types, their construction and the standards used in hydraulic hoses. We will learn everything through a practical example and with a stamp method. So by the end of this video, you will be able to select and specify the hoses for almost every hydraulic system. Now, whenever we think about selecting the hydraulic hoses, the first thing comes in our mind is pressure rating. We usually say that the hydraulic hoses pressure rating should be at least 1.5 to 2 times the working pressure of the system, so that the hoses can safely transmit oil even under uneven operating conditions, like pressure spikes due to shock loading. But this logic is only true for pressure line. Let's understand it with an example. In this hydraulic circuit of a press machine, the hose connecting the pump to the directional control valve and from directional control valve to the hydraulic cylinder are the pressure line. So if the working pressure of the system is, let's say, 100 bar, actually it's better to consider relief valve pressure. So if relief valve is set 10% higher, so at 110 bar, and we apply a factor of safety of 2, so the pressure rating becomes 220 bars. Now, if you see the hose catalog, pressure ratings are usually defined in megapascal or PSI. So 220 bars becomes 22 megapascal, or approximately 3200 psi. Now let's look at the return line. The return line connects the directional control valve back to the tank. Here we do not need a highly pressure rated hose because the pressure is only the back pressure caused by the flow resistance in hoses, filters and anything in between the line. Typically, the back pressure is only around 1 to 2 bars, regardless of the system working pressure. So for return line, we can use much lower pressure rated hoses, something around 2 to 5 bars. Now, the most important line, the suction line, the line connecting the tank to the pump inlet. Here, the pressure is completely different. It's not positive pressure, it's actually negative pressure, vacuum pressure. So we need a hose that is rated for vacuum pressure to prevent hose collapse. We will discuss suction line in detail in a separate video, but to select the right hydraulic hoses, pressure rating alone is not enough. To fully define the specification of any hydraulic hoses, we follow an industry standard method called a stamp. S for size. This means the internal diameter of the hose. T for temperature. This includes both fluid temperature and ambient temperature. Incorrect temperature rating leads to fast aging and loss of rubber flexibility over time. A for application. This describes how the hose behaves in operation, whether it is static or moving or exposed to vibration or abrasion. Based on that, we select the hose's construction, not just pressure rating. M for medium. This means the fluid carried by the hoses. that is hydraulic oil. P for pressure. This is the maximum working pressure, including pressure spikes. Some industries use an extended form called stamped, where E stand for end fittings and D stand for delivery or flow rate. For hose selection, stamp is sufficient. E and D relate more to overall system design. So let's start with size. Hose size simply means the internal diameter of the hose. In hydraulic hoses, sizes are specified in inches. Here, do not confuse with BSP size or any fitting size. This is purely internal diameter of the hose. In industry, hose sizes are also expressed using dash size. 1 dash equal to 1 by 16 of an inch. So 1 inch is dash 16. 3 by 4 inch hose is dash 12. Half inch will be dash 8 and so on. Now comes to the main question. How do we calculate the required hose sizes of hydraulic system? So to calculate the hydraulic hose sizes, we start with a basic formula of fluid mechanics. The flow rate equation, flow rate Q equal to cross-section area A into fluid velocity V. Now, in any hydraulic system, the oil flow is delivered by the hydraulic pump. And whether it's a gear pump or a piston pump, they all are positive displacement pumps. That means they deliver nearly constant flow regardless of any change in pressure. So the flow rate remains constant in this equation. That means if we increase the hose cross-section area, then to maintain the constant flow rate, the oil velocity decreases. If we decrease the hose diameter, the oil velocity increases. This can be also felt intuitively. In this simulation, when I am increasing the hose diameter, the oil flow velocity slows down. And when I am decreasing the hose diameter, the oil flows faster. And as the flow rate is independent of the pressure change, so no matter how much I am changing the pressure, there is no effect on oil velocity. Now, in this equation, the flow rate is in cubic meter square per second and the section area A is in a square meter. But in hydraulic system, the flow rate is usually expressed in liter per minute, LPM, and hose diameter in millimeter or inches, not in meter, of course. So let's convert the unit. After unit conversion, the equation becomes flow rate in LPM equal to 0.06 into area in meter square into velocity in meter per second. And as we are aiming for hose diameter, and since the hoses are circular, so we can drive this equation for hose diameter. So hose diameter in millimeter equal to 4.61 into square root of flow rate in LPM divided by oil velocity in meter per second. And this is the single most important equation for the hydraulic hose sizing. Let's understand this with an example. From pump sizing video, here the calculated flow requirement of hydraulic cylinder is 42 lpm, but the selected pump delivers 46.11 lpm at motor speed 1450. So let's consider the flow rate 46 lpm for our calculation. And yes, without knowing the pump flow rate, it is impossible to estimate the hose sizes. This is the first step of the hose size. More about flow rate calculations in this video. Now the question is, what should be the oil velocity in hydraulic hoses? So the short and simple answer is there are recommended oil velocity range for different type of hose lines. But even more important question is, why do these recommended velocity exist? And to understand this, we need to revisit some basics of fluid mechanics. First, in our flow rate equation, The oil velocity we calculate is average velocity. But in reality, fluid do not move at the same speed everywhere inside the hose. The fluid layer closest to the hose wall has nearly zero velocity. This is called no-slip condition. And as we move from the wall towards the center of hose, the fluid velocity gradually increases. So the fluid at the center has the maximum velocity. So if we plot the velocity profile, it's formed a parabolic curve. And because different fluid layer moves at different speeds, they rub against each other. This creates internal frictions, which results in viscous shear stress. This shear stress resists the flow of oil, and to overcome this resistance, we lost the pressure along the length of hose. This loss is called pressure drop. The pressure drop can be calculated using Darcy-Weisbach equation. In laminar flow, the pressure drop is directly proportional to oil velocity. That means if velocity doubles, pressure drop will also double. However, if oil velocity increases beyond a limit, the flow no longer remains laminar. It becomes turbulent. In turbulent flow, fluid layers start mixing. It becomes chaotic, and which increases the friction drastically, and pressure drop becomes much higher. In turbulent flow, it becomes proportional to the square of velocity. That means if velocity increases 2 times, the pressure drop increases 4 times. So our goal should be keep the flow laminar inside the hydraulic houses at any cost. Yes, pressure drop will always exist whether flow is laminar or turbulent. This is the nature of fluid flow, and it cannot be completely eliminated. It can be just minimized. So over the years of experiences, engineers have identified these oil velocity ranges, where the hose sizes, means the cost, and the pressure drop are optimally balanced. But these velocity ranges are not specific to every grade of hydraulic oils. So selecting these recommended oil velocity do not guarantee laminar flow for every grade of oil. Because whether the flow is laminar or turbulent do not depends on oil velocity alone. It actually depends on ratio of inertial force to the viscous force of oil flow. This ratio is called Reynolds number. If Reynolds number is less than 2000, the flow is laminar. If Reynolds number is greater than 4000, it's turbulent. And between 2000 and 4000, the flow is transitional and it can behave either laminar or turbulent. And from this equation, we can clearly see the Reynolds number depends not only on velocity, but it also depends on fluid density and fluid viscosity. And the hydraulic oil density and viscosity varies from one oil grade to another. So it is possible that at same velocity, in same size of hoses, one oil can be laminar and other can be turbulent. This is why even after sizing the hose using recommended velocity, we must check Reynolds number and ensure it remains below 2000 for a specific hydraulic oil being used. So here is a final simple sequence for sizing of any hydraulic hoses. First, start with simple flow rate equation and calculate the hose size based on given flow rate and using recommended oil velocity range. This gives a good starting point. Next, select the closest standard hose size. Then check the Reynolds number for selected hose size. If the Reynolds number is less than 2000, the flow is laminar and the hose size can be finalized. If the Reynolds number is greater than 2000, increase the hose size by one standard size and recheck the Reynolds number. And repeat this until the Reynolds number remains below 2000. Ensure the laminar flow. Let's understand this with an example. So the pump oil flow rate is 46 rpm. And for pressure line, the recommended oil velocity is range 3 to 6 meter per second. Now, here is general practice. If the pressure line is long, has multiple bends, or the application is heavy duty, we should select lower velocity, range about 3 to 4 meter per second. If the pressure line is short, simple routed, and application is medium to light duty, we can go higher, 5 to 6 meter per second. For our application, a medium duty hydraulic press with simple routing. So let's select the oil velocity 4 meter per second. Now putting the values in equation, the calculated hose diameter comes out to 15.63 millimeter. This is non-standard hose size. So we will choose 19 mm, 3 by 4 inch. But this is not final yet. We need to check the Reynolds number. Now, the Reynolds number is usually expressed using dynamic viscosity. But in hydraulic system, we typically use kinematic viscosity in centi-stokes and hose diameter in millimeters. So the Reynolds number equation can be simplified to Reynolds number equal to velocity in meter per second into diameter in millimeter into 1000 divided by kinematic viscosity in centi-stokes. For this 20-ton press, we will use hydraulic oil 68, means kinematic viscosity will be 68 centi-stokes. Putting the values, the Reynolds number comes out to be approximately 1118, and this is well below the limit of 2000. So the flow is clearly laminar. So finally, the pressure hose line internal diameter is 3 by 4 inch, 19 mm-12 size. Now, even after understanding all these calculations, you might say that in my application, I'm using a very heavy-duty piston pump that is capable for higher pressure, let's say 400 bar. And I have selected the hose pipe without doing any detailed calculations. So even if there is a pressure drop in hoses, how much can it really be? Maybe 10 or 20 bar. That is not the real problem. The system will still work. So yes, the system will work, but the pressure drop is not only the problem. First, the pressure drop represents a loss of hydraulic energy, which is converted into heat, and the heat cannot convert back into hydraulic energy. So this is the permanent power loss. Second, increase in heat reduces the oil viscosity, which lowers the system efficiency and accelerates the seal and hose degradation. Third, higher velocity creates flow noise, vibration, and hammering effects, which can damage the valves, fittings, and other components in line over the time. This is why the proper hose sizing becomes critical in hydraulic system. And now let's understand how to select the hose part number from the manufacturer catalog. In this video, we will select hoses from Parker, a well-known hydraulic hose and fitting manufacturer. Now, to select the hose from manufacturer catalog, hose size alone is not enough. We must need stamp. First, the size. From our calculations, the required hose size is 3 by 4 inch. Next is temperature. For our application, the ambient temperature is factory environment is around 45 to 50 degrees Celsius. And in a hydraulic press, the oil temperature can reach around 70 degrees Celsius. However, most standard hydraulic hoses are designed to operate from minus 40 degrees Celsius to 100 degrees Celsius. Otherwise, for higher temperature, there are series which can take up to 150 degrees Celsius. In our case, a standard hose series is sufficient. Next is application. Application helps to decide the outer core and reinforcement type of the hose. In our case, the routing is fixed. Also, there are no tight bending constraint and also no any abrasion or sliding contact. So a standard outer hose is acceptable. Next is media. Media defines the inner tube material of the hose. Here the media is hydraulic oil 68. So a standard hose nitrile rubber inner tube is suitable. Next is pressure. We have already calculated the required pressure rating, 22 megapascal. Now we have almost all the required information. Now, if you look at the house manufacturer catalog like Parker or Gate, you can find these manufacturer catalogs in video description. So you will notice in some house series, the pressure rating remains constant for all house sizes. And there are also some series where the pressure rating decreases as the internal diameter of the hose increases. So why does this happen? So the reason lies which house standard being followed. Most manufacturer follows two different standards. One is SAE and other is ISO. Now under SAE, J517 is construction based house standard. That means it defines how the house is built. Almost all hydraulic houses are built using three basic layers. The first layer is inner tube. This layer is directly contact with the hydraulic oil. Its job is to seal the fluid and guide the flow. It must be compatible with the hydraulic fluid. It also has to withstand temperature and chemical attacks from additive in the oil. This layer do not carry the pressure strength. This is only contain the fluid. For hydraulic oil and petroleum-based fluid, the inner tube is usually made of nitrile rubber. For other fluid and chemicals, the inner tube is selected from the compatibility chart in catalog. The second layer is reinforcement layer. This layer is most important layer from pressure point of view. It carries almost all internal pressure. There are three common types of reinforcement. The first is textile reinforcement. This is used for low pressure houses, typically for return line, drain line and pilot line. These houses are light and flexible, but their pressure rating is limited, 3 to 5 bar. Second type is wire bead reinforcement, which is the most common. Higher tensile steel wires are beaded over the inner tube in one or multiple layers. Most standard working pressure houses fall in this category and widely used in industrial and mobile hydraulics. The third type is spiral wire reinforcement, used for very high pressure applications. These hoses are stiffer, so having a large minimum bending radius. Now the third layer of the hose, the outer cover. Its job to protect the reinforcement from external damage, such as abrasion, moisture, and heat. If the outer cover is cracked or wear out, the reinforcement gets exposed and house life reduces very quickly. Now under SAE J517, these constructions are classified into 100R series. 100R1 is for single wire bead. R2 is for double wire bead, commonly used for pressure line. R12, R13 and R15 are spiral wire for very high pressure, and R4 is for suction and return line. Now comes to the important point, that is why for these series the pressure rating is decreases when the hose sizes is increasing. So as the internal diameter of any hose increases, the hoop stress at the hose circumference also increases. And in a given SAE hose series, the wall thickness and reinforcement constructions remains the same for all the sizes. So to keep the hoop stress within safe limits, the allowable internal pressure must be reduced as the hose size increases. This is why within the same SAE hose series, with same reinforcement, the pressure rating decreases as the hose size increases. And because of this, SAE standard assign pressure limits separately for each size of the hose of the every hose series. And the hose manufacturer must need to meet or exceed the defined working pressure rating. Now let's look at practical example. Parker 302 series is based on SAE 1000R2. It has synthetic rubber inner tube, 2 layers of high tensile steel wire bead, and it's suitable for hydraulic fluid. So our required hose size 3 by 4 inch. Part number is 30212. The working pressure rating is 21.5 megapascal, 3100 psi. This satisfying our pressure requirement. So we can select this hose. Now another popular hose standard, ISO 18752, also known as constant pressure hose. This is a modern performance-based standard. So instead of asking how the hose is built, ISO asks what pressure the hose can survive and for how long. So ISO 18752 defines the hoses by constant working pressure. Classes such as 1000 psi, 2000 psi, 4000 psi, and so on. And in a series, every hose size has same pressure rating. So you can ask that why does pressure rating of these hoses not decreases as the hose size increases? So the reason is hose construction changes with the size. As the hose diameter increases, the wall thickness and reinforcement, such as the number of steel beads or spiral layers, also increases. And this allows the hose to maintain the same constant pressure rating across the different sizes. Now, for our application, we need working pressure of about 22 megapascal, which is roughly 3200 psi. So select a 400 psi series. From this catalog, this corresponds to 3 by 4 inch hose. The part number is 48712. So this hose meets our size requirement, our pressure rating, and also our application condition. And now let's move to return line hose sizing. And here you might ask that IU's oil is returning to the tank here. So pressure drop is not critical at all. So why do we even care about return hose sizes? So yes, in return line, the pressure drop is not critical as compared to pressure line. But the velocity of oil still matters. Higher oil velocity in return line can generate turbulence inside the tank, cause foaming. Foaming means air entering in oil, and air is enemy for the hydraulic system. It damages the pump valve, seals, and reduce the system life. And this is why the return line oil velocity must be kept lower. The recommended oil velocity for return line is 1.5 to 3 meter per second. Let's select the value of 2 meter per second. Now putting the values in equation, hose diameter comes out to be 22.1 millimeter. It is always better to go one size higher, which is 25.4 millimeter. So we will select 1 inch -16. Now let's quickly check the Reynolds number. It comes out to be 747, which is well below 2000. So flow is fully laminar. And now let's talk about pressure rating. So as we discussed earlier, in return line, the pressure is only back pressure. Typically, the pressure is around 1 to 2 bar. Now, in catalog, you will find separate hose series designed especially for return and suction lines, which follows SAE 1000R4, is commonly used for return and suction line application. For 1 inch size, the hose is 811-16 with a working pressure of 0.5 megapascal, perfectly suitable for our return line. Now, the most critical hose line in any hydraulic system, the suction line. And the suction line hose sizing need a deeper understanding of how a pump actually works. We all believe the pump sucks the oil from the tank, but this is not true. In reality, the oil is pushed into the pump by the atmospheric pressure, and that makes the suction line sizing extremely critical. So I will cover suction line sizing in a dedicated separate video.
As a professional machine design engineer, learning has always been a serious part of my work. Not for any exam, but to actually understand the concepts deeply and apply them in real design problems. And this is not limited to mechanical core subjects alone. But for us, we also need to understand the mathematics, physics, logical thinking, and even the coding, because all this directly affects how we think, analyze, and solve the problem. The problem is the most traditional learning of these subjects are heavily depends on textbook, long derivations, memorizations, and passive reading. Although I don't even need to memorize these subjects, but I actually need to understand them deeply so I can apply them in real engineering. And that's exactly where Brilliant comes in. Brilliant helps us to reach serious learning goal by focusing on understanding, not memorization. Instead of watching lectures, you actively solve the problems, change inputs, and observe how the system behaves. For example, in Brilliant maths and physics content, you build intuition for topics like mechanics, vectors, digital circuits, and logical thinking by interacting directly with the problems. This kind of learning actually changes how we think, not just what we remember. Another important part is personalization. Brilliance adopts your level and pace, so difficulty grows with you instead of overwhelming you. The daily learning structure makes it realistic to stay consistent. You return every day, strengthen your fundamental, and gradually transform the way you approach the problem solving. So, if you want to become smarter every day and build a strong foundations, check out Brilliant. Go to brilliant.org/master mechanical design. You can also scan the QR code on a screen. With a premium subscription, you get unlimited daily access to all courses and problem sets. If you sign up with my link, you will get 30 days free plus 20% off the annual premium subscription. And also thank you Brilliant for sponsoring this video.